Good morning, student. In this session, I will discuss the thermodynamics of the micellization process. You have already studied the structure of the micelles, the driving force responsible for the micellization process, as well as the ionic and non-ionic surfactant. Now I will discuss thermodynamics of the micellizations. Now, with the help of thermodynamics of the micellization, one can determine different thermodynamic parameters like free energy of the micellization, enthalpy of the micellization, entropy of the micellizations. And on the basis of all these values, you are able to predict that micellization process is spontaneous process, as well as whether it is an entropy driven process or the enthalpy driven process. Basically, there are two models available in the literature. One is called mass action model and another is phase separation model, or sometimes it is called pseudo phase model. So today I will discuss both the model, and bear in mind that you should determine the mass action model or phase separation model for ionic surfactant as well as the non-ionic surfactant. So I can start with the thermodynamics of micellization. It is divided into two models. One is mass action model another is the phase separation model. And we will do for non-ionic and ionic surfactants. And what would be the application? That with the help of this model, we can calculate first the standard free energy of the micellization. We can calculate the standard enthalpy of the micellization as well as standard entropy of the micellization. So let me start with this first, the mass action model for non-ionic surfactant. So let me start with this simple system. N of surfactants. It is actually monomers. Monomers. Is converted into micelles. It is micelles. And small n is the aggregation. It is aggregation. I am doing for non-ionic. We know that the Km Micellization constant is equal to M S N. We know that delta G of M is equal to minus RT natural log of Km. And it is free energy. Free energy of micellization. And standard free energy of the micellization per monomer is equal to delta G divided by N. This is standard free energy of micellization per monomer. Okay. So now I have to substitute the value of Km from here. So I can write delta G M is equal to minus RT natural log of M, and you can write like that also. Or I can write like that. G of M is equal to minus RT natural log of Mn. Here it is plus, because it is minus, here is minus RT. Sorry, this is N RT natural log of S. Now, if I want to write the standard free energy of the micellization per monomer, so that is actually N, so that is natural log of M, and plus this N is divided this N, so it is RT natural log of S. As because the number of, if N is greater than 50, most of the cases, if I am talking about this, it is almost very high, and the value of this Mn because it actually it is the micelle, and it is the monomer where it will form this type of micelles, maybe very high number. So that is actually, that can be considered as a CMC. And in as comparison to the value of dissociation constant, this is very low, it can be neglected. So I can write that delta G, the first thermodynamic parameters, is equal to RT natural log of CMC. That means if you know the CMC value, so for example, if I am taking the CTAB, which is CMC is approximately 1 millimole, 1 into 10 to the power minus 3, and SDS approximately 8 millimole. And if I am talking about the 27 degrees or any temperature, so you can calculate the free energy. And if I just convert it into log, so it will be delta Gm is equal to 2.303 RT log of 1 into 10 to the power minus 3. And R, you can, the SI unit or CGS unit, if it is 8.31 per joule, so in terms of joule. So, but the solution is that every time we will get negative value. It is negative value. That indicates that, and that is also true, that the micellization process is the spontaneous process. But sometimes what is the problem? Because sometimes if the value of CMC is very, very low for the non-ionic surfactant, so we should take this concentration delta G of M is equal to RT natural log of XCMC. That is actually mole fraction unit. Mole fraction unit. And if I take the concentration is moles per liter, so I have to concentration of that CMC or the CMC in terms of moles per liter divided by molar concentration of water, which is approximately 55.44 approximately. You all know, if I consider in 1 liter of the water and the molecular weight of water is 80, so 1000 divided by 80, so it is, so either you can determine the delta G value with the help of simple, just substitute the value of the CMC, temperature and R value, you can get the value of, or better you can use the value of in terms of mole fraction. Now this is the first parameter, which is called the free energy of the micellization. Again I am talking, this is for the non-ionic surfactant. Now the second parameter is called enthalpy. And another parameter is the delta S standard. Now we all know that delta G is equal to delta H minus T delta S. You all know these things. This is one form of the Gibbs-Helmholtz equation. So I can write like that, minus T delta S M standard is equal to delta G M minus delta H. Or simply, so second parameter is delta S M standard. This is equal to delta H M minus delta G M divided by T. So this is the second parameter. First parameter is this. So 1 and 2. But again there is a problem. How do I calculate the delta H? In order to calculate the delta S, we need delta H as well as delta G from this. So again I have to calculate the delta H. We know that there is a relation, very common relation, because there are various forms of the Gibbs-Helmholtz equation. One of the form is, I think you know these things, delta G capital T is equal to minus delta H by R T square. It is one form of the Gibbs-Helmholtz equation. But if I substitute the value of delta G here, so it will d by dt. Delta G is equal to, we know, RT natural log of CMC T is equal to delta H. I can write here, now it is Micellization process. So this T is cancelled. So again I can write in first part here. So what I can do, of course minus is there. It is minus. So what I can do, so RT square d by dt natural log of CMC is equal to minus delta H standard M. So this is the third formula. So by that method, you can determine first delta G, then delta H, and then delta S. Now one problem is there, that how do you calculate that this d by dt log of CMC? So it is nothing, it is actually temperature dependence of the CMC. That means you have to calculate CMC various temperature, and you have to plot a graph between natural log of CMC and T. Suppose you are getting such type of plot. So the slope is d by dt of natural log CMC. So this is the experimental method by which you can determine all these thermodynamic parameters for non-ionic surfactant. But there is some standard instrument that is called the isothermal calorimeter, thermal calorimeter, ICT method also there. So by calorimetric method one can directly determine the enthalpy. And once you determine the enthalpy, entropy, and free energy of the micellization. You can predict, yes, this system is spontaneous or the system is entropy driven, and the driving force can easily be determined. Of course, all these values depends upon the various factors. If you change, if you add some electrolyte, if you add some solvent, so naturally the values of these thermodynamic parameters may change. So now I will proceed for ionic surfactant, but almost the formula will be same. Only thing is that because if I take the ionic surfactant, you all know that there must be some head group, there is tail group, and there are some counter ions. So counter ion plays some role in this values. So we have to consider that counter ion. Rest is exactly same. First you calculate delta G, then you calculate delta H, then you calculate the delta S. Okay. So let me now solve for the ionic surfactant. Again, it is mass action model, not phase separation model. It is mass action model. So let me solve. So it is now ionic. And method is mass action model. It's very simple and you can solve with the help of CMC. You can determine the different types of value. Now if it is a ionic surfactant, so naturally there is a difference. What is that difference? First difference is that it may be negatively charged, it may be positively charged, and additionally there is some counter ion. I can write it is a G. Again it may be G, it may be negative. And then of course, and number of counter ions I can write that N. So this G is counter ion. Now if I take suppose anionic surfactant, if I take anionic surfactant, so I can write like that N S negative. If I take sodium dodecyl sulfate, I can use like that sodium ion M, that means Mn is also negatively charged, but it depends upon the N minus M like that. Here also I can write like that N S negative N minus M G plus Mn. It is negatively charged. So it is for ionic type of surfactant. So now I will take a general term. So I am taking N S negative M G is counter ion M and N minus. So exactly same, just like your non-ionic surfactant, K M is equal to M N We should not worried about this thing because generally it even cancel, it is constant value, but we should careful about these things. Yes, don't worry about this minus or this. Don't worry about this minus or plus, and exactly same, just like your non-ionic surfactant. So same thing, first we will write the delta G of micellization, same thing, minus RT natural log of Km. So we have to substitute the value of Km from here. So we can write like that, delta G of M is equal to minus RT natural log of this like things. Yes, N. You can write plus minus, it's absolutely no problem. So if I write like that, there are so many methods. Delta G standard of M. This is equal to, so you know that what should I write? I can write like that, minus RT. If I write like that, you can write like that. If I just like that, minus RT natural log, or in minus M, you can write like that, N. But we are least interested in this. Again, here it is also minus, so I can write like plus N natural log of S. Again, plus, because here it is minus, M natural log of G. Or what I do, I can take common. What is common? That I can write in the red color, RT by N is common. Okay, because delta G by N. So I first write N natural log of S plus M natural log of G. You can write plus also. Then this part is actually that in non-ionic also you have seen that micelle formation with the help of single term. So that in right hand side equation, that part can be neglected or cancelled. So it is up to you. You would like to write, or you need not to be worried about this term, because it is a micelle formation part, and most of the cationic surfactant, the value of N is very high, more than 60 or 70. So that part is also neglected. And another assumption is that because counterion is also plays a very significant role, and it also take part in the micellization process. So therefore, if this concentration is very high, so that natural log of G plus or minus whatever it is also considered as a CMC. It is also considered as a CMC. And of course, this is also considered as a CMC. So what we do, so RT because this is divided by N, divided by n, RT log of CMC, because if I just divide it by this n plus m by n natural log of CMC. What I can do, again red color, RT natural log of CMC 1 plus m divided by n. So what is the difference between normal non-ionic surfactant and ionic surfactant? In non-ionic surfactant, delta G m is equal to simply RT natural log of CMC, and here there is one additional term, that is 1 plus m divided by n, RT natural log of CMC. So in this m by n is m by n is nothing but degree of counter and binding. And one can determine the degree of counter and binding by take a plot of log CMC with respect to the counter ion concentration and concentration of surfactant with the concentration of the counter ion, log CMC and the concentration of counter ion. And most of the cases, as you know, that if it is a perfect surfactant, so there are 100% counter ion binding. That is equal to the value of beta is equal to 1. If it is 100%, but most of the cases it is in between 0.6 to 0.8 degree of counter and binding. So if it is 1, the value of m by n is equal to 1, so it is 1 plus 1 is equal to 2. So that I can write 2 RT natural log CMC, or in some time we can write it is 1.8 RT natural log CMC. So that means what should be our formula? It is 1 plus m by n RT CMC, because the degree of counter and binding, it depends upon the types of the surfactant. So before applying this delta G value, one should determine the degree of counter and binding. So depending upon the values, but in normal cases you can write 2 RT natural log of CMC, or it is actual. So, and fortunately there is no change in delta S value, because it is like delta H m minus delta G standard m divided by T. So for non-ionic and ionic this same, but for delta H what we have, minus RT square dy dt of natural log of CMC. For that, just here is also in place of RT square 1, again we can write 1 plus beta. So then according to the types of the surfactant, you just change it. So it may be 2 RT squared dy dt CMC. So what do I summarize? That whether it is a non-ionic surfactant or it is a cationic or ionic surfactant, almost all these thermodynamic or micellization parameters are same. Only thing is that you have to consider the degree of counter and binding. Now the last part is that the another method, that is called the phase separation method. So it will take only 2 minutes. It is called the phase separation method. Why it is called phase separation method? Because, and it is sometimes it is called the pseudo phase model, because one phase is monomer phase, another phase is micelle phase, and we actually consider the chemical potential. So here we consider the chemical potential. So chemical potential of monomer you can or surfactant phase, and you can consider the M phase also like that. M or small m, it makes no difference. That is standard chemical potential of this is equal to this. And you know that chemical potential is nothing but the partial molar free energy. So you know that the change in free energy with respect to number of moles at constant pressure, temperature, other moles, G bars. So in normal cases, in delta G of micellization, maybe minus QS standard. That is also possible. So if you determine the chemical potential of the Micellization phase and chemical potential of the monomer phase, we can calculate the delta G. And once you calculate the delta G, rest of the things are same thing. And it is again it is a common, is equal to mu S of 0 plus RT natural log of activity of. This is for surfactant phase and or monomer phase. Again mu of m or small m you can write like that, mu of m plus RT activity of micelles. And same thing is the micelles, and when micelle is formed, we not consider these things like that. So the difference between the standard you can call it, mu of m standard, mu of s. This is nothing but the delta G of standard. And in normal cases, again it's an assumption that the chemical potential, standard chemical potential of S and S equal to 0, this thing. And so we can consider the RT natural log of S. And here is the same natural log of CMC. So whether it is a phase separation model or mass action model, you can determine the delta H, delta S and delta M. So in next class, I will discuss some of the results. With the help of CMC value, we will calculate the delta G, delta S and delta H, and then we will interpret the thermodynamics of the micellization. Thank you very much.